Hey everyone! In this video we're going to be talking about some more algebra problems. This will be the last sort of proper lesson for the algebra unit. So before the winter break we went over some problems involving one variable and some problems involving two variables, and now we're at the point of we've already reviewed those things in the new year. So we're going to continue with one more lesson of some practice problems. And what I've done is so we're going to do three problems in this video. The first one involves just one variable. The third one involves two variables. And the one in the middle, you can solve it either way. So the first one is going to be just no word problem. I'm just going to give you the equation and we'll just go from there. Same thing for the third one, but for the second one, the one in the middle, it's a word problem, and I'm going to show you that on the word problems you can choose to solve it with one variable or with two. It depends on what you want to do. So I'm not going to put word problems on the test that you have to solve with two variables. Solve it whichever way you like, but I'll show you in this video how you can choose whether to do it with one variable or with two. One of them you might like the organization of one of them better, or you might find that using two variables just gets too confusing and you don't want to do that. But I'll show you, and then we'll go from there, and you guys can decide on the test which one you want to do. So let's begin. I'm going to put down a title of let's see, this is what, lesson 41. This is Algebra Practice Problems. So just in general, some algebra practice problems here with both one and two variable questions. So algebra practice problems. Let's get started. Once again, I'm going to number the problems with Roman numerals. So I'll label them that way, because when we're doing the two variable ones, then I like to use the actual numbers 1 and 2 for the equations themselves. So that's why we've got the Roman numerals going here. All right, so first question. This one we should hopefully zip through because it's one variable. That's easy stuff by now. So the equation that you're given is 4x plus 3 equals 6x plus 9. All right, and what we want to do is we want to solve for x here, right? We've only got the one variable, so we're going to have to solve for x. So to do that, well, let's follow the procedure that we got down a couple of lessons ago, which was to get all of the variables, all of the terms with variables on one side of the equal sign. So it's your call if you wanted to bring the 6 over here or take the 4 over there. So like the 6x, bring it to the left and make it a negative, or take the 4x to the right and make that a negative. Now you might notice that if I bring the 6x over here, then I'm going to end up with 4x minus 6x. Don't write that down, because that's going to give me my term with the variables has a negative sign. If you're fine with it, go for it. I prefer the term with the variable to be positive, so I'm not going to do it that way. But what that's going to mean is that I'm going to have to take the 4x over to the other side. So in my next line, this one you can write down. This one will be 6x will stay there. But then this 4x, when we take it over to that side, is going to be subtracted. So it's going to be 6x minus 4x. Now I'm not going to write down the 9 on the right side, because we want to bring that over to the left side, because we've got all our variables over there, so we want to bring all the numbers over here. So that means this 3 on the left side is going to stay. We want the 3 on the left side, so we'll leave the 3 right there. I'm just moving it over so that I got room to put the 9 in here. Now when I bring this 9 over, the 9 will go here, no problem, but because it's being added on the right side, when I bring it over the equal sign, it's going to be subtracted on the left side. So looks like we can't escape having a negative number either way in this question, because either it's going to be the numbers that come out to a negative quantity or the ones with the variables that come out to a negative quantity. So if we go ahead and we do the subtraction, on the right side we get 6x minus 4x, which is going to be 2x. Nice, we got a positive number over there. And then on the left side we've got 3 minus 9, which is going to give us negative 6. Make sure you don't do it the other way. and write it as 9 minus 3, because that'll give you a positive 6 over here, which is different. So we want this to be negative 6 in this particular question. So the last step is to solve for x itself. So now we've got it down to just one term with an x in it, and it's being multiplied by this 2 right here. I don't want it to be multiplied by the 2, I want it to just be x. So to do that, I'm going to divide this side by 2. That means those 2's will disappear. But if I'm dividing by 2 on that side, I have to divide by 2 on this side. And so on the right side, I'm going to be left with just x. That was the whole point of doing that division. But over on the left side, well, we've got a negative quantity divided by a positive quantity. And I'm not sure if we talked about this in the first few lessons of the school year, but for multiplication and division, if both signs are positive or both signs are negative, your answer will come out to be positive. If you've got one of each, then your answer is going to come out to be negative. And that doesn't matter if you're doing multiplication or division. If you've got the plus sign over there or over here, as long as you've got one of each and the operation in the middle is either multiplication or division, your answer is going to come out to be negative. So what we can do to get that negative answer, or like to find the answer, is we can ignore the minus sign to start. We'll just do 6 divided by 2, which is 3. And then we just stick the negative sign back on. So we ignore it, do the division as though there was no negative number at all, and then just stick the minus sign back onto the 3 at the end. So then there's your answer. For this one, it'll be x equals negative 3. I just cut through the 3 with my box there, but hopefully you can still read that, no problem. So we've got x equals negative 3, and you can always go back and check your answer with that starting equation by plugging in negative 3 wherever you see an x. So if you plug it in over here, you'll get 4 times negative 3, that's negative 12, plus 3 is negative 9, so this side should come out to negative 9. And if this side matches, then that tells us that we've done the right thing. So 6 times negative 3 is going to be negative 18. Negative 18 plus 9 is going to be negative 9. So we've got negative 9 on both sides if we plug in this x equals negative 3. So that should be the right answer then. Alright, hopefully that makes sense. I'm going to erase the title before I do the next problem because it's a word problem, so I'm going to try and make use of the space. And then I'm going to see if I can write it a little bit smaller than the last one so that we can actually keep the text on the board while we're solving the problem. So this is the problem that we're going to solve in 2 ways. So let's see, so we got a little 2, that's for problem 2. So I'm going to do like a 2A and a 2B. So like a Roman numeral 2 with an A, and then after that I'll do Roman numeral 2 with a B. So you guys can label it the same way if you want in your notes, or you can write it differently, whatever works for you. Alright, so for this one, let's see, what do we have? Okay, Trent, inspired by the Liverpool player, Trent is looking for new shoes. Trent is looking for new shoes. All right. He buys a red pair. Well, I mean, when he finds the shoes, he buys a red pair and a white pair. All right, so he's got a pair of red shoes and he's got a pair of white shoes. Now, the white pair is $12 more expensive than the red pair. Okay, so the white pair is $12 more expensive than the red pair, and the total cost, I'll put a comma there instead of a full stop, and the total cost is $44. Should have made that $66 for his jersey number, but that's okay. We'll keep it at 44. find the cost of each pair of shoes. So find the cost of each pair. Okay, so there are two ways that we can solve this problem, and we'll see if we can squeeze them both in here. Probably not at the same time, but I'll do like a 2a, the first way that we can do it down here, and then I'll erase 2a, and then we'll do 2b in the same space. So 2a, we would need a let statement for this because this is a word problem, so we haven't been given any of the variables. So let's say, for me, if I'm choosing a variable to represent one of the numbers, I usually pick the smaller one because then I can express the other one as like x plus something, right? So if I've got two numbers, like if the red pair is cheaper, right? So if I say let x be the price of the red pair, then I can say that the white pair is going to be x dollars, whatever the red pair costs, plus 12, because the white pair is $12 more expensive. So I can say then x plus 12 is the price of the white pair. And I haven't written it yet, but you could put in a thing for both of these that says that specifies that it's in dollars, right? And that each of those prices are in dollars. So it's going to be x dollars, not x cents, not x pesos, not x rubles. So we've got that x is the price of the red pair, and we got x plus 12 is the price of the white pair. So right now we're just working with one variable. We've only defined what x is, and then x plus 12, that's fine. It's still just one variable. So now what we got to use one more piece of information. Right now we've used the fact that the red pair and the white pair, right now we've used that the white pair is $12 more expensive than the red pair, and that the red pair costs some amount of money, which is x dollars. That's not particularly helpful yet. So what we need to do is we need to use one more piece of information, which is that the total cost is $44. So in order to set that up as an equation, well, we know that the red pair plus the white pair is going to cost $44. So that means x plus 12 should equal $44. So then I can say x plus 12 equals 44. So this x right here is for the red pair, and then this x plus 12 over here is for the white pair. If I thought this through a little bit better earlier on, I would have taken out a red marker so that we could sort of color code this a little bit better. But so that first x comes from the red pair, and then this whole x plus 12 comes from the white pair, and the total cost is $44. So now if we go through and solve, well, we get that x plus x is going to be 2x, and I'm going to throw the 12 over to the right side because I want all the numbers over there. So it'll be 2x over here is equal to 44 minus 12 over there, right? It's positive on the left side, so it'll be negative on the right side. So then if I go, let me move this up over here somewhere. So then we've got 2x is equal to 44 minus 12, that's going to be 32. I'm hoping I've done my math right. And so then to get to x, we just have to divide this side by 2 so that we can have those 2's disappear. And then we'll divide the other side by 2 as well. That'll leave us with just x on the left. And 32 divided by 2, that's going to be 16 on the right. Now I'm running out of space here, so I'll just talk about this, and you can write it down if you want, and really you should write this next bit down. So I'm running out of space, and I don't want to erase a bunch of stuff just yet, because I'm going to use some of this information when we solve it the second way. So I'm going to leave everything on the board as it is right now, but what we haven't put yet is a therefore statement. We haven't, well, there's a couple things we haven't done. Right now we've just got x equals 16, which is all of the math that we needed to do, but now we need to answer the actual question. Find the cost of each pair. Well, we know x is the cost of the red pair, right? The red pair is going to cost us x dollars, and we know x is equal to 16. So the red pair is going to cost us $16. The white pair is going to cost us x plus $12. Now we know x is equal to 16, so 16 plus 12, that'll be 28. So then you would write a therefore statement that says, therefore, the red pair costs $16 and the white pair costs $28. And if you really wanted to show it, you could put in an extra little line that says, x plus 12 is the white pair, and then, replace the x with 16, and so then you can show that you've got 16 plus 12 in there as well to show how you got the 28. All right, so the therefore statement is something that we haven't put in yet, but it's something that you should put in your answer. I'm just a little bit short of space on the board right now. So what we're going to do now is I'm going to erase the little 2a, we'll make that a 2b, and we'll solve it a slightly different way. So right now we just solved it with one variable. Now we're going to solve it with two variables. So I'm going to get rid of the second let statement. So unfortunately, because you guys aren't working on a whiteboard yourselves, you're going to have to recopy out that first let statement. But while you do that, I'm going to write down the second let statement over here. So we've got, so let x be the price of the red pair. Now for the white pair, I could have said x plus 12, or, well, it's a different pair of shoes, so I might as well give it its own variable. We can say let y be the price of the white pair. I hope that's legible. I'm writing at more of an angle than I normally do. So let x be the price of the red pair and let y be the price of the white pair. So now we've got two variables that aren't really related to one another. But what you could do from here is you can say then, you don't really have to, you can just start writing down the math, it's not a big deal. But you could say then, we know that the red pair plus the white pair is going to equal $44. Oh, once again, this, you could have a thing over here that says in dollars, or you could have it as how many, what am I doing? In dollars. You could also have it just like the red pair in dollars, the price of the red pair in dollars, the price of the white pair in dollars. I forgot to do it that way, which is why I've done it with the brace bracket here. But you don't have to worry too much about that. So we know that the red pair plus the white pair, x plus y, is going to give us the total. So we know x plus y is equal to $44, right? And we also know that y, the white pair, so the cost of the white pair, is going to be $12 more than the cost of the x. The red pair, x, right? So we know the red pair cost x dollars, plus 12 will give us the white pair, the cost of the white pair, right? So we've got x is the cost of the red pair, but for the white pair we know it's going to be $12 more, so we add 12 to it, and we get that y is equal to x plus 12. So then here you could say that this is your equation 1, and this is your equation 2. You don't have to put the 1 and 2 there, because now it's like, it looks like it's part of the equation. So if you are putting the 1 and 2 there, put a circle or a box around them so that you can tell that they're not part of the equation. So the equation is just x plus y equals 44 and y equals x plus 12. And so now we've set it up as a problem of two variables and two equations. So then you could solve it that way. Now I would, in order to solve this, I would take this second equation, y equals x plus 12, we'd sub it back into that first one. So we'd look at equation 1, and anywhere we see a y, we'll replace it with x plus 12. So when we do that, we sub equation 2 into equation 1, and what you get is that you have the first x, that's fine, nothing changes there, but then this y we're going to replace with x plus 12. So we've got x plus 12 equals 44. We don't have to change anything on that side. And if you notice, that is the same equation that we got at the beginning of 2a when we were solving it as just an equation of one variable. One equation, one variable. This is the equation that we got, right? Red was x, and then white was x plus 12. So we just did x plus 12 equals 44, and we just solved it that way. So the difference here isn't so much in the math, it's more in the setup. So if you wanted to give the cost of the white pair, a more proper name than just x plus 12, then you could do it that way, because now you can think of it as I have to solve for x and I have to solve for y. X is the red pair, y is the white pair, or you could, you don't have to stick with x and y. You could say r is the red pair and w is the white pair. And solve it that way, just to remind yourself that you need to solve for both of them. Because if you only define one variable x, and you're only using that one variable x, it's really easy when you get to the end of the problem to forget that that's only for the red pair, and you still need to solve for the white pair. So setting it up with two variables can be handy if you're being asked to find both of them. But you don't have to do it that way. So if it's more confusing working with two variables and you're confident that you won't forget to fully answer the question and write down both answers, then feel free to do it with one variable. If you like the organization that comes with doing it with two variables, you can do it that way. Although some people, they'll look at the setup here with x and y and then look at these two equations and they're like, I would never be able to build these two equations out of that setup. Then if the first way looks easier, you can set it up that way. Just try to remember that you have to answer the question. Go back and reread the question when you think you're done and ask yourself, have I done what the question asked me to do? And if you have, great. And if you haven't, well, you're not done yet. All right, so that's two different ways to solve this type of word problem. Not every word problem is going to lend itself the two variable option. So you won't necessarily look at just any given word problem on the test and be like, oh, I'm going to do this one with two variables. There might not be a proper option to do it with two variables, or there might not be a practical option to do it with two variables where it just makes way more sense to do it with one. So obviously if you solve it with two variables, if you solve a word problem on the test with two variables and I was expecting you to do it with one, that's fine. Hopefully you guys won't get your marks docked for that. Now obviously I've been writing the tests and teaching the classes, but I'm not marking the tests. So I'll have solutions copies and stuff, but the actual marks that you guys are getting is kind of out of my control. But hopefully you will not be docked marks if you solve it one way instead of the other. So when I make the solutions, I'll solve it both ways. For the questions that I think you should be solving, or for the questions that I think you could reasonably solve with two variables instead of one, I'll have a solution for both of those so that you guys can see the two different methods, and when it gets marked, that you guys don't get docked marks for doing it one way or the other. Because I don't want you to be forced to use a single method. As long as you get the right answer, it's all good. You don't need to solve it a specific way. If you prefer doing it with two variables, that's fine. If you prefer doing it with one variable, that's fine too, as long as you get the right answer. As long as you're still getting that $16 and $28, at the end of the day, it doesn't matter how you got there, right? Now, showing a little bit of work is important, because if let's say instead of saying 16 and 28, you got 18 and 26, right? So you're off, your math is off by a little bit. That would be where showing your work and writing down these things like let statements and stuff, that's where you get your marks. Because if you just write down, 18 and 26, if it was right, you might get full marks or mostly full marks. But if it's wrong, you get absolutely nothing, right? If it's a question that's marked out of 4 or 5, and you get 1 mark for a let statement, and 1 mark for setting up the equation, and 1 mark for actually doing the math, and 1 mark for your therefore statement, then it's a lot clearer. And if you mess up somewhere in the math, well then, okay, at least you had a let statement, and at least you had a therefore statement, so I can see that you're okay, the red pair costs this much, and the white pair costs this much. Then, you'll get some of the marks for the question. So even though you did the math wrong, you might come out with 2 out of 4 or something like that, or maybe 3 out of 4. Depending on how close you were or where you made the mistake. But if you just write down 16 and 28, you might get all the marks depending on like in the future if you're taking more math courses where you're having tests like this, then you might get all the marks for just having the right answer, but you're taking the risk of if you have the wrong answer, you're not giving them any other information for which they could give you part marks, right? The question could be out of 4, and if you've messed up any little part of your calculation that you did in your head, you get 0 instead of getting 1 or 2 or 3 marks out of the 4. Right? So that's why showing your work is important. That's why all of this stuff is really important. The therefore statement is good to have. The let statements are good to have for, if somebody's marking your tests and some of you are using X and Y and some of you are using R and W or A and B, or my university brain is suggesting like X subscript 1 and X subscript 2, like X1 and X2, or it's just, there's so many different ways you could name the variables and stuff that if you're going through marking test after test after test and everybody's using different variables and not explaining them, it makes it harder to mark, it makes it harder to understand, right? So if you're doing a math problem with the intent of somebody else seeing it, you definitely should write down as much of the explanation as you can. Like my assignments for my university courses, the actual math might only be like 3 or 4 pages of work, but my explanations will be another 10 pages. So I'll end up submitting 15, 16, 17 page assignments where only 3 or 4 pages of it is actual math and equations, and everything else is me just talking through the process and writing down paragraphs of this is what I'm doing, and this is why I'm doing it, and this is what it represents, all that stuff. It's all really important for having other people understand the math that you're doing. All right, so that's enough babbling for now. So let's do one last question. This one will hopefully be a little bit more straightforward because it's not a word problem. So this is question 3 like the Roman numeral 3. And I'm going to give you 2 equations and we will solve for the 2 variables. So again, we'll stick with X and Y, and on the test I'll stick with X and Y. I don't want to throw you off with something silly like that. So equation 1 is going to be 14x minus 3y equals 14y minus 3x. I actually wrote it the other way around in my notebook actually, but that's okay. It doesn't change anything. So 14x minus 3y equals 14y minus 3x. And equation 2 is 2x plus y equals 36. Now, don't write this part down just yet. You might be thinking, all right, let me look at equation 2, and we'll do y is equal to 36 minus 2x. Brilliant. And then I will take the 36 minus 2x, and I will sub that in up here for y, and I will sub that in over there for y. We'll do the distributive property, so because you'd end up with like 14 times 36 minus 2x over there. Right, when you sub in this for y, you're going to have this big honking thing attached to that 14, so you're going to have to do this multiplication. 14 times 36, you can work that out. It's just a bit of a mess. So it looks like the logical step is, okay, well, we got a y sitting here by itself, so let's isolate that y completely. But I wouldn't solve this problem that way because that's a little bit messy. I'm going to show you a different way to go about it, and there's no wrong way to do it. It's just there's messier ways and some more compact, neater ways to solve these problems. Some problems are easier to solve in one way than another, and so I'm going to show you maybe the easiest way for this one. It took me about 3 lines to solve it this way, showing my steps, and you'll hopefully appreciate the simplicity of this problem when you notice the game plan. So we're going to look at equation 1. Hang on, let me make this plus sign proper. All right, there you go. So we're going to look at equation 1, and we're going to notice that we've got the x's and y's all mixed together. So let's see if we can just simplify equation 1 so that it's something that's a little bit more manageable for us. It's something that we can work with. So the way I would do this is I'm going to get all the x's on one side and all the y's on the other side. And so see if we can simplify that down to just one term with x's and one term with y's. So if we do that, so we're just going to working with equation 1. You could say like work with, I'm just squeezing that in here, but work with equation 1. So then I'm going to bring the 3x, the minus 3x that's over there, I'm going to pull that over to the left side so that it becomes positive 3x. So this 14x will stay, and then we're going to have that 3x over there come over, so it'll be 14x plus 3x, plus because it was subtracted on the right side, so when I bring it over, it'll be added on the left side. And simultaneously, I'm going to take this negative 3y, and I'm going to throw it onto the right side, where it's going to become positive 3y. So the 14y that's already on that side can stay, so we got 14y, and then this 3y, it's negative on the left side, so when I throw it over there, it becomes positive. We get 14y plus 3y. Great, so now we've got all the x's on the left and all of the y's on the right. So now let's do the addition. So we've got 14x plus 3x, that's going to be 17x is equal to, and then we've got 14y plus 3y, that's going to be 17y. Alright, so this looks kind of promising, like this is already a lot simpler than the starting equation, but let's see if I can get rid of this 17, then I would have just x is equal to something on the other side. So if I divide this side by 17, then these two 17s will disappear, and I'll be left with just an x on the left side, right? But if I'm dividing by 17 on the left, I have to divide by 17 on the right. And if I do that, those 17s cancel, and I'm left with just y on the right side. So this problem is almost the exact opposite of 2b, the one we solved as a 2-variable problem. You could have done it as a 1-variable problem, and we made it a 2-variable problem. This one is a 2-variable problem. I've given you 2 equations and 2 variables, but really it's 1 variable. X and y are equal to the same value. That's what this equation right here is telling us, is that x is equal to y. So I could write all x's up here, I could write all y's up here, I could swap out all the y's for x's and all the x's for y's, and nothing will change because they're all representing the same value. So what I'm going to do is, because the 2 variables are equal to one another, I'm just going to throw out the y, and we'll just use x for the rest of the problem. So now we can sub this, let's say we call this equation 3, then let's say we sub equation 3 into equation 2. And this labeling it as equation 3 is totally allowed. Before, when we were rearranging the equations slightly and we were like, this is our new equation 2, you're allowed to call that equation 3. You could call it equation happy face. As long as whoever's marking it can understand which equation you're talking about, you could use stars and circles and triangles and colors for your equations. I just number them with 1, 2, 3 or ABC, something like that, something relatively simple, but you could do whatever you want, and if you're making new equations like this one, give them a new name so that you can refer back to them and talk about them later in the problem. So here we're going to sub equation 3 into equation 2. So we know x is equal to y, so basically all I'm subbing in is anywhere I see a y, I'm going to throw it out and replace it with an x up here in equation 2. So we had 2x plus y is equal to 36, but I'm replacing all the y's with x's, so that means it's going to be 2x plus x is equal to 36. Right, so we get, instead of 2x plus y is equal to 36, it's now 2x plus x is equal to 36, which, if you wanted to go the other way, you could have replaced the x over here with a y, and then it would have been 2y plus y is 36. So, same idea. Now, this equation is already set up for all of the variables are on the left side and the numbers are on the right side, so I'm just going to do that addition. 2x plus x will be 3x. That's not a 3 or an x. 3x equals 36. And now to solve for x, we're just going to take that 3x equals 36, and we're going to divide the left side by 3 so that we can get rid of that number in front of the x. So we're left with just x on the left side, and then on the right side, we would have to divide that side by 3 as well. 36 divided by 3 is going to leave us with 12. So there we go. We've got an answer for x. X is equal to 12. And Now, because it was set up as a two-variable problem, we should also say what y is equal to. Now, we know from our equation 3 over here that y is equal to whatever x is. So if x is 12, y has to also be 12. And you can just write that and put it in a little box, and that's it. End of the problem. Now, you can always go back and check to see if it makes sense in both equations. Second one might be a little bit easier to check. We've got 2 times 12 is 24, plus 12 is 36. Yep, that one checks out. Up here, it's a little bit more complicated because you've got to do 14 times 12 over here. 3 times 12, that's going to be 36. But what we do know is that this is going to be 14 times 12, right? And this is going to be 14 times 12 because x and y are both 12. And then we know this here is going to be 3 times 12, and this here is going to be 3 times 12. So without actually doing the calculation, we can see that these two sides will end up being identical as soon as we sub in the numbers. And you don't even really have to solve them at that point. You can tell that they're going to be the same thing. So that's it. That's the 3 problems for today. Maybe 4 if you consider that word problem as 2 questions because of how we solved it. But anyway, that's that for this lesson. I'm going to put out a really brief video for sort of the structure that I'm planning for the test. I still need to write the test, but just the way I'm thinking of going about it, just so that you guys know, what to focus on, what to expect, what to study. Yeah, other than that, that video will hopefully be no more than about 5 minutes. You guys can use the rest of this class, or if you're watching this at the beginning of a class and you still got plenty of time, watch the test review, and then you can get cracking on just studying for this test, which will be out in the next couple of days. All right, cool. So if you guys have any questions, as always, get in touch with me. Otherwise, I will see you in the next one. Have a good one.